Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone. Welcome to Learning by Solving Problems Session 3, Carboxylic Acids, Organic Chemistry 2. The relative acidities of carboxylic acids have been used to compare the electron donating and electron withdrawing properties of substituents. These studies are particularly valuable to distinguish between inductive and resonance effects on the stabilities of compounds and ions. Here is some examples. The pKa of phenylacetic acid is 4.31, showing that phenylacetic acid is a stronger acid than acetic acid with pKa 4.74. Is the phenyl group electron donating or electron withdrawing in the ionization of phenylacetic acid? B. The phenyl group is a mild ortho para-directing group. In electrophilic aromatic substitution, is the phenyl group electron donating or electron withdrawing in the electrophilic aromatic substitution? How can you resolve the apparent contradiction? 4-methoxybenzoic acid is a weaker acid than benzoic acid, but methoxyacetic acid is a stronger acid than acetic acid. Explain this apparent contradiction. Methyl groups are usually electron donating, and propanoic acid is a weaker acid than acetic acid. Yet 2,6-dimethylbenzoic acid is a stronger acid than benzoic acid, but 2,6-dimethylphenol is a weaker acid than phenol. Explain these confusing experimental results. Recall from Organic Chemistry 1 the substituent effects on ions. These effects found to be a combination of resonance and the inductive effect. We use hydrogen as a standard and is regarded as having no effect. Electron donating group can be recognized by lone pair on the atom adjacent to or by system, like OCH3 when we have here on the oxygen lone pairs. Except R group by inductive push the electron far away from it. AR and vinyl by electrons. So here we have what we call it positive inductive effect, where the group pushes the electron far away from it, like alkyl. Here, electron donating group via the lone pair. Or if we have bi system like aryl or vinyl, when the bi bond can donate the electrons, okay, and stabilize the carbocation. Stabilize the carbocation, destabilize the anion. On the other hand, electron withdrawing group can be recognized either by the atom adjacent to the bi system having several bonds to more electronegative atom, or having a formal charge, positive or partially positive charge, like the carbon here on the carboxylate and the nitrogen here in the nitro group. So if we have electron withdrawing group, we have negative inductive effect by the electronegativity of the atom in here stabilizes the anion. Again, if this group multiple bond has electronegative element in here, so that the multiple bond will withdraw the electron towards it and stabilize again the anion, and we call that negative mesomeric effect. Negative mesomeric effect. Since there is no p orbital overlap between phenyl and the carboxylate anion, because of the presence of CH2 in between, the increased acidity must be pure inductive effect. And we can conclude that phenyl has electron withdrawing inductive effect because electron withdrawing group decreases the electron density on the oxygen and stabilizes the carboxylate. So if we are finding that the phenylacetic acid is more acidic, means that its conjugate base is more stable via induction, that must be electron withdrawing group. So we can say loudly that phenyl has electron withdrawing group by induction, has negative inductive effect. From this experiment, we have found that phenyl group is electron withdrawing group by induction in part A. In case of electrophilic aromatic substitution, for the biphenyl like example, electrophile will be attacked by the double bond, forming an intermediate sigma complex. Carbocation in here is connected to the pi system of the other phenyl group. Well, and this phenyl group will stabilize the carbocation in here by delocalization with what we call it here donation, but via mesomeric effect. So phenyl group found to be also para and has a positive mesomeric effect stronger than the inductive effect, negative inductive effect, and stabilizes the carbocation intermediate via what we call it again electron donating positive mesomeric effect. Let's try to find out interpretation for why para or 4-methoxybenzoic acid is weaker acid than benzoic acid, while methoxyacetic acid is a stronger acid than acetic acid. Well, let's examine first benzoic and para-methoxybenzoic. The methoxy group, oxygen has lone pairs, 2 lone pairs, and can donate that to the through the pi system to the carboxylate, right? And by doing that, it is destabilize the anion. Destabilize mean that keeping the equilibrium this way and having this weaker acid because the conjugate base is unstable. Okay, so the dissociation will go this way. pKa of benzoic acid is smaller than the pKa of para-methoxy benzoic acid. In here, the methoxy acetic acid, we have here CH2, so the lone pair in here isolated, but the electronegativity of the oxygen will work via inductive, so it will be electron withdrawing effect on the carboxylic acid, okay, and of course will stabilize its conjugate base. That's why pKa 3.83 stronger acid than acetic acid. Via induction, there is no mesomeric effect. Metal groups are electron donating. That's why propanoic acid is a weaker acid than acetic acid. So again, by induction, okay, by induction, the methyl group will destabilize the carboxylate ion, making this weaker acid. It's 4.87, while in acetic acid pKa is 4.74. Again here, the methyl group by induction, positive inductive effect, will destabilize the O- conjugate base from the phenol, making it weaker acid. It's 10.73, while in phenol it's 9.97. Now, coming to the benzoic acid, 2,6-dimethyl benzoic acid is a stronger acid than acetic acid. Okay? In benzoic acid, we have here carbon with pi system, so there is p orbital, and here again we have p orbital. They are connected together, so we can see clearly that we have resonance structure, positive charge in here and negative charge in here. That's via mesomeric effect. Okay, so that will destabilize the conjugate base out of it, because if we get this out, H out, so we have double anion, and that's highly unstable resonance structure, low contribution. So in benzoic acid we can find delocalization of electrons. There is a resonance. Okay, phenyl ring and carboxyl group are in the same plane, so benzene is able to donate electrons by resonance, overlaps through parallel p orbital. This stabilizes the acid and destabilize the carboxylate anion conjugate base and make the acid weaker. Okay, in case of 2,6-dimethyl benzoic acid, the methyl groups at 2 and 6 positions prevent the carboxyl from coplanarity with the ring. You can see it, it's not coplanar with the ring. So there is no resonance to stabilize the acid, and the carboxyl group sees the aromatic ring only as electron withdrawing group via inductive effect, which enhance acidity. One will say, okay, we have methyl and we have phenyl. Okay, on this substituent, apparently the slight electron donating effect of the methyl groups is overpowered by the strong electron withdrawing inductive effect of the benzene ring. So the carboxyl will see this whole group as electron withdrawing group. See you next session.